Hello, this is the Exam 3 review slides for Fall 2021. These will be covering the alkyne reactions, the conjugated systems along with Diels-Alder, as well as the aromatic systems. So for some of the reactions for the alkynes, so typically what's going to happen with these is that it's going to be similar to the alkene reactions, except you're just going to be doing them twice. Okay? So to synthesize an alkene, one of the things you can do is you can have adjacent halides on there and just perform essentially two E2 reactions. The first one would make the double bond, and then the second one would make the triple bond. With adding HX or XX across there, you literally just add it across the triple bond. Okay, so if there is a preference where there's, for HX, right? Remember the halide's going to go on the higher ordered side. Okay, remember that, but they are going to end up on the same carbon. Now, when you get down to the oxymercuration and hydroboration, they're still going to have the same preferences as far as higher, with the oxymercuration one going on the higher ordered side, and the hydroboration one going on the lower ordered side. That's really only an issue if it's a terminal, right? So for here you've got primary versus secondary. Here they're both secondary, so you're going to get a mixture of putting it on either side. Okay, there's no preference. Here there is. So for oxymercuration, you're going to put the carbon on, or the oxygen on the higher ordered side. For hydroboration, you're going to put the oxygen on the lower ordered side. Now, you're going to, after the first time, you're going to put the oxygen on that double bond. That's not stable, and it rearranges itself into a C double bond O. So wherever that oxygen is going to go, that turns into a C double bond O. So if you're doing oxymercuration, it usually ends up with a ketone. If you're on a terminal alkyne and you do hydroboration, you're going to end up with an aldehyde. So this is a nice way of making an aldehyde. Okay. Now with alkynes, when you're doing hydrogenation, right, if you're just doing straight palladium on carbon, there's no it's going to end up going all the way, because you're going to be adding double bond or hydrogens across here. The alkene, after you first do the first time, the alkene is going to get produced, but that is still reactive towards the palladium, so it goes down to the single bond. So if it's just a regular hydrogenation, you're going to end up going to the single bond. If, however, you poison the catalyst either by adding quinone to make a linear catalyst or barium sulfide, you're only going to be able to do that once. Okay, and so the hydrogens end up on the same side, right? So remember, hydrogens go on that same face. So you're going to make the cis alkene. To make the transalkene, you usually do what's called a Birch reaction, which is Birch reduction, which is you either use lithium and ammonia as a solvent, or you use sodium in there. And so with this one, you're going to get one up, one down, and so you're going to get the trans double bond. Okay. Now for the oxidative cleavage reactions, okay, so for here the ozone or the permanganate, that's going to again cleave those bonds, and you're going to replace that carbon-carbon triple bond by 3 CO bonds. And the way you do that is having the carboxylic acid on both sides. Now the problem is, if it's a terminal alkyne, you're still going to be making the carboxylic acid, but those aren't stable, and so you're going to lose this as CO2. Okay, so it's going to eventually get further oxidized to carbonic acid, which then breaks down into CO2, and I guess technically water. So you have to be careful with oxidative cleavage at the terminal. So now these are the reactions that we use for doing the synthesis. Okay, so for terminal alkyne, use sodium amide. Now don't get the NaNH2 confused with sodium NH3. Those are two different compounds. Here, it's solid sodium and NH3. Here, it's a salt. It's a combination of sodium and NH2 put together. Okay, this is a very strong base. It can remove the terminal hydrogen on here to make the carbanion, and that can do a nice little SN2 reaction here. All right, so it's simply just an SN2 displacement, and you're going to make this new bond here. Now for the Diels-Alder reaction, okay, so you have your diene here and your dienophile, and so this is going to end up there, this is going to end up there, and that's going to end up there. And so what ends up happening is for this one, so you've got these two methyl groups here, because they're on the same side of this alkene here, that means they're going to go one way. And so for here, we said, okay, well, this is going to be a wedge. Okay, so what that means is the hydrogens that are on this side are going to be at a dash. And so you would have hydrogens here, like that. Now you will always end up, so these carbons here are these carbons here. These two carbons here are these two carbons here. And the bond that we're making is this guy right there. Okay. Now for this one, we do it the exact same way. However, because we've got a cyclic diene, okay, we have to make a choice. Right? So typically for this one, so for this bridging carbon here, it's got to get out of the way. And so I typically put it on a wedge. It doesn't matter which way you do it. Okay? But what you have to do is you have to look at the groups that are the four groups that are hanging off of your dienophile here. And so if any of those has a, not counting the alkene, but if any of these groups have pi bonds on them, what's going to happen is those groups are going to want to go the opposite way of however you wanted this one to go. And so here's the pi bond, and so what this means is this guy here wants to go on a dash, which means, right, these guys have to go on a wedge. Because this one has to go in the opposite direction of this one, this methyl group has to go the same way, right, because it's on the same side. And so you end up with this. Another way of drawing it would be like this. Right? And so here's our bridging methylene here, CH2. So here's these two carbons, right? Carbon, carbon. We have our two hydrogens that are on a wedge. And then we have on the dash, we've got the aldehyde and the methyl. So you can either draw it like this, or you can draw it like this. Sometimes students see it a little bit easier than this. So, right? And so these are the these are the bonds that we made. Those are those new bonds right there. Okay. Okay. Now, so if we're doing this, we have an excess of HBr, right? With that, and so for this one, right, we're going to be adding across the double bond. Right, so with that, so this is secondary, this is primary. Right, so with that, so with HBr, the bromine is going to go on the higher ordered side, and since we have a triple bond, we're going to do that twice. Oops. Let me make this a little bit easier, right? Because remember, there's a hydrogen here. It's already there. And so what we're going to do is we're going to add, right, bromine here, hydrogen here, and then add another one because we're going to do it a second time, bromine, hydrogen there. Okay. Now for this one here, right? We have a triple bond, but we have palladium, okay, but the we have barium sulfate, so it's poison, so it can only go one step. Now remember, so I usually draw these as a sawtooth, but the way that this would tip is actually how it actually is, because this sp carbons are actually linear, it would actually look like this. Right, you sawtooth there, but this is linear. And what would end up happening is you would have these hydrogens add on the same face, and so what you would end up getting is you would get a this is drawn poorly, but you would end up with them on the same face. So you would end up with cis. So I accidentally flipped it over. So about that, but you need to add these to the same face. So it's this one just flipped over. There you go. Right. So don't forget, here are those where those hydrogens would be added. Now with this one, predict the products. Now, for this one, we don't have a cyclic diene, so it doesn't. We just have to. So it's a little bit easier figuring this out. So that goes there, that goes there, that goes there, and so we're going to start with our. Because we know we're going to make a cyclohexene. Okay. Now there's nothing really hanging out except for hydrogens here, so there's nothing that's going to be here. With these two carbons, right? If we say this is the wedge side, then that means this side is going to be the dash. Okay. So there's a hydrogen here. There's a hydrogen over here. So for this one, right? So here's those two carbons. Right? So I'm going to say this ketone's on the wedge. Right? Hydrogen here. And then this side of the dienophile is going to be a dash. So hydrogen here, methyl there. And that's it. Same thing down here. We're going to start with our cyclohexene. Now there is a methyl group hanging off of here, so you want to start with that. And then there is this bridge here. Right? And so we're going to say, okay, I'm going to put this on a wedge. So if that's on a wedge, then that means we have to look on our dienophile, right? So here's our hydrogens. We have to look for something that has carbon double pi bonds on it of these four groups. Here's our pi bond here. So that means this side, this has to go the opposite way of this one, which means this whole side is going to go that way. So if that's a wedge, this has to be a dash. Okay? Which also means this side would also be a wedge, right? Because it's got to go the opposite way of this one. Okay? So since we've designated that CH2 there as a wedge, then that means these guys have to be on a dash. Which means that hydrogen's on a wedge. Okay, that's a really bad wedge. You could draw it either way. It doesn't matter. Okay, so what would we need to synthesize this? Well, okay. So the dienophile is always opposite where the alkene is. So that means the dienophile here it is here. Okay, which means these other four carbons, that's the diene. So these are the dienes. And since there's not really anything hanging off of them, that is just going to end up being this. Here are the two carbons here of the dienophile. And notice how these two groups are both on wedges, so that means they have to be on the same side. It doesn't matter which side, as long as they're on the same side. And the other two would be hydrogens. Right? So that would be this. Now for designing a synthesis, for this one we're going to have to build the carbon skeleton, right, and make sure that there's a chlorine that goes in here. So the best way to start is to, well, just take a quick look, right? We've got the alkyne, so we're probably going to need to go through alkenes or alkynes. Okay, So the way that we know how to put a chlorine on there, and we're just thinking about this just in general. Okay, so if we have this, right, so we know that if we were to add HCl to it, right, typically this is done in excess. The problem is what we're going to end up happening is we're going to end up putting two chlorines on here. Okay, so we're still going to get the 2 hydrogens here. Okay, but we're going to get 2 chlorines. So the easier way of doing that, okay, is to go through the double bond. Okay, right, and HCl excess. So for this one, right, we only end up adding 1 chlorine. Right? Now, you have to be careful, because what you don't want to do is you don't want to have it like this. Okay? Because, right, so let's say you have it like this. Because remember, this is, right, this is secondary and this is secondary. So there's no preference. And so what you would end up getting would be a mixture of products. You would get where half the time the chlorine would go here, and the other half the time the chlorine would go here. Well, we want to try to avoid that. Okay? And so by putting the double bond at the end, we can have secondary versus primary. We can have some preferences. Okay? And so in order to just have it make this product, okay, where it's methyl group at one end and then methyl group and then chlorine, what we're going to have to do is we're going to have to build the molecule so that there's a double bond there. So the last step is going to be just adding some HCl to it. So this is what the last step has to be. Okay. Now, how do we build this one? Well, how do we put in a double bond? Well, we know that we have to go through a triple bond. Okay, and so what we can do is the easiest way to do that, okay, would be to go through this one here. Right? If we go through a triple bond to a double bond, we can either do a Birch reduction, which is lithium and ammonia. Because there's no cis or trans in this one, it doesn't matter. Or we can go through like H2 Lindlar. It doesn't matter which. So for this one, it doesn't matter which one you do. You're just going to go from a triple bond to a double bond. Okay. Now for this one, what's going to end up happening is we're going to have, this is the bond. So now we've got a triple bond. Aha. So we can use this, and then we need to add these 4 carbon pieces here. And so since this is where the bond is, this is where we're going to do the attachment. On the other side, it needs to be a hydrogen. Okay, so that means we're going to be using this one here. Okay. So those are those 2 carbons, and then for this one, right, we're going to need a 4 carbon piece, which is here. Right, that's a 4 carbon piece. So here's our 6 carbons. And so how do we synthesize this? So we're going to take our acetylene here, hit it with sodium amide, NH2. Right? That's going to rip off one of these hydrogens. Okay? And in this case, it doesn't really matter which one. Right? And we're going to make plus NH3. And then what we end up doing is we end up dumping in this 4 carbon piece. And that synthesizes this. So here is the actual synthesis here. Starting with acetylene, ripping off the hydrogens, right? Ripping off that hydrogen to make the carbanion. That will then do an SN2 to displace the bromine, making that bond there. You can then convert that into a double bond from an alkyne to an alkene, and then do HCl to synthesize that. So you need to think about the second half of the synthesis first, and then you know where you're going for this part. Okay. Now for this one, it's going to be, you're going to be using Beer's law, which is the absorbance is equal to this molar absorptivity, okay, or extinction coefficient, times the path length times the concentration. So for the absorbance, right, it's 0.025. Right? The molar absorptivity is 6,300. The path length is 1 centimeter. And then C is what we're solving for. Okay, and so when we do this, we're going to divide both sides by 6,300. So C is 0.02 divided by 5, 6,300. And so we end up with this value here. So you can either put it into just scientific notation where your calculator gives it to you, or you can be all fancy and put micro, right? Because micro means times 10 to the minus 6. Okay. So usually you get 3 of these values, and you got to just find the 4th. So for this one, okay, so we're going to, the way you solve these is exactly the same. Okay. Okay, so first thing you're going to do is you're going to take these, right, so we're going to draw in the hydrogens, just so it's a little bit easier to see. Okay, we're going to take one of these double bonds, attack the hydrogen, and then kick away the chlorine. And so what you're going to end up getting is you're going to end up with this. Now we want to put the hydrogen here so that the carbocation can be here. Right, plus Cl minus. The reason for that is this allows us to do a resonance structure where we shift the bond over there, and so we can get the CH2 there, right. So that puts the positive charge there. And so our chlorine is going to attack wherever it sees a positive charge. Okay? And so it's going to either attack here or it's going to attack there. So for that first one, right, we're going to make this product. Now you don't have to draw in the hydrogens. I'm doing that just because I think it's easier to see. There, Cl. If instead it attacks here, right, we're going to get keep my colors consistent here. Add that there, and the chlorine is going to go there. Okay. Now I'm just going to do this just so it's a little bit easier to distinguish it, because what can happen is, so these are the first two products. You can also have this double bond instead do the same thing. Okay. When that happens, you get you're going to get the hydrogen adding. You want to put the positive charge adjacent to that double bond so that we can get a nice little resonance structure. Right? We can move that over there. That there. Oh, I forgot to put in the chloride. Okay. So again, the chlorine is going to attack wherever it sees that positive charge. So it attacks here, then we're going to get this product. Hydrogen here, right, chlorine there. If instead it attacks there, double bond there. Right, we're going to get the hydrogen there and then the chlorine right there. So those are your 4 products. So you do it the exact same way each time. Now, is it aromatic? Okay, so it has to have. So remember, it needs to be a ring, okay? And everybody in the ring needs, right, a p orbital available. So that means you're either part of a pi bond, you have lone pairs, lone pair electrons, or you have a charge. Okay? And you also need the Huckel number. Okay? Now, the Huckel numbers will tell you whether it's aromatic or anti-aromatic. Okay? Now remember, benzene is sort of the ultimate aromatic compound, and that has 6 going to it. And so what we do is we go back and forth, and so we can go 6 to 8, down to 10, 12, 14, 16, and so on and so forth. But you can also go backwards, right? So 4 and 2. Okay. So if we look at this first one, right, we have, if we count them up, 2, 4, right, so that, so everybody has a ring, everybody's part of all the carbons are part of a pi bond, and so it has 4 total pi electrons, which would say, this is anti. So for this one, right, 2, 4, 6, right, everybody has p orbitals, right, it's 2, 4, 6, so this would be aromatic, right. So for this one, right, the oxygen has lone pairs, right, the carbons have pi bonds, so, and it's a ring, so we're good. Some of that, but for this one, remember with if you have a heteroatom, you can hide it so that it becomes aromatic. And so what's going to happen is it's going to take one of these, so this would be 2, 4, 6, and then it's just going to hide the other one. So this is going to be aromatic. So for this one, right, we are in a ring, however, we do have this CH2 here. And so for that one, what's going to end up happening is, it doesn't matter if we had, 4 or 6 or whatever, the electrons can't keep moving around. Okay, so that makes this one be non-aromatic. Now, one of the things you want to know is you will need to know the base names. I don't know. So I don't know what happened here, but this is supposed to be a CH3 at the end. So somehow the benzene got moved down. So but that's OCH3 for anisole. Okay. So but that. But you want to know what those base names are. Okay. But that's so. We won't do proper naming, but at least know what those are. Okay. So for the rest of these slides, what you're going to want to do is you're going to want to go through these, check out what I've whether that's writing or it's a square like this, because that's the information you're going to need to know for the multiple choice questions. So with that, okay. Well, good luck.